This is a lesson video for 9-6. First, there's some of the tips and reminders from working in the circumference section 9-5. So if you did not get some of these reminders, also that one that says it's never acceptable to, please make sure you're identifying if you're doing that, where you're performing a calculation and getting the result, like 24 divided by 2 is 12. But then realizing that you need to multiply it by something else, you tack that on. And that isn't okay math, because by transitive property, you'd be saying that 12 and 12 pi were equal. And since they aren't, things like this need to be two separate calculations. 24 divided by 2 is 12. And then a separate calculation that talks about what 12 pi is. Okay. So just make sure that we have good algebra. We're not writing any false statements mathematically that make it look like we don't know better or that we don't have that understanding. So the warm-up. You may or may not have ever seen this if you went to State Fair, but this is a picture of my daughter years ago standing next to a monster truck or monster tractor tire attached to a monster tractor. And so what I looked up was about how big those tires are, and they're 66 inches in diameter typically. Your standard automobile tire for most four-door cars, two-door cars is typically measured in centimeters, so I had to do a little conversion. The average car tire's diameter is almost 25 inches, 24.69. So your warm-up question, you please pause the video and work this out and show good math and noting what you're doing. How much farther would that monster tractor tire travel if it turned 5 turns, that tire rolled 5 full turns away from my daughter, versus if a standard car tire had rolled 5 full revolutions or turns away from her? How much farther would the tractor tire have traveled? So pause the video, calculate, annotate, and come back when you're ready to check. If you're back, get some information to check here. In 5 revolutions, the average car tire, you can see how far it would have gone. In 5 revolutions, again, every revolution travels a circumference because each piece of that circumference of the tire hits the earth. And so if we were exact, it would roll 206.55 pi inches farther. To the nearest inch, about 649 inches, which means if it had rolled away from her, it would have rolled 54 feet farther than the car tire. So pause the video, correct things, go over things, recalculate things, chat with your neighbor if they're also working this and having some questions. When you're ready for the lesson video then, resume the video. So 9.6 is the last big idea in the circles chapter, and the last big idea in calculating is called arc length. And what they're saying is instead of arc measure, which tells us how many degrees around the outside or the center of the circle that arc is taking up, which is really like a ratio of how much of the 360 degrees, or we can put it into a ratio. Arc length wants to know the actual length of string it would take to cover up that arc. So pause the video, work on these questions about the Allen Bradley Clock Tower in Milwaukee, and get a calculator, record what you do to get these, and come back when you're done. If you're back, and forgive the handwriting, this was smartboard handwriting. So some things we knew about the Allen Bradley Clock Tower, they told us that each clock hand is 20 feet long, so we're talking about a radius of about 20 feet. And so how far does that minute hand travel in a day? Well, in a day there's 24 hours, and in degrees, 360 degrees per rotation, and the minute hand goes around 1 time per hour. So measured in degrees, it would be 8,640 degrees. That would be the same for the clock here in our classroom, that in degrees, its minute hand travels 8,640 degrees. What would be different, however, between the two clocks is what if that were measured in feet? What if, and forgive this ridiculous explanation, we strapped one of you to the end of that minute hand on the Allen Bradley clock, safely so that no harm would come to you. If you could do that, you on the end of that minute hand would travel around 24 times in the course of the day, and you would go 24 circumferences around, and in feet, since our radius is feet, you would travel 960 pi feet. And if you're wondering about how big that is, think about that pi is a little more than 3, so that's more than 3,000 feet. You're a little about 3,015, almost 3,016 feet. You're talking about more than half a mile in distance. Certainly that wouldn't be the case if you were attached to the minute hand on the clock here in our room, because its circumference is smaller. So while you would still travel 24 circumferences, those circumferences, or arc, would be smaller. So how many feet does it move between 3 and 324? We figured out that if you're looking at 4 minutes of clock time, you're looking at 24 minutes of clock time. You're looking at 24/60ths of circumference as what fraction of circumference we'd be taking. And therefore, every 24 minutes out of 60 would represent that we'd only want part of the circumference that clock minute hand goes around in 1 hour. So you'd be looking at 24/60ths, or 4/10 of 40 pi, 16 pi feet in those 24 minutes. And again, pause this, add to your notes, make sure you have good ideas and good understandings before you proceed. The idea that you're getting from that 3 o'clock to 324 idea, is what's called arc measure. An arc measure, by definition, you can see here, it's the number of degrees or radians, and radians is a measurement you're going to get to next year. So for the moment, you could cross off the radians. We will leave radians for the other unit of measure for angles that you will use in trigonometry. But it's the number of degrees taken up by a circle's arc. We've done that arc measure then, also matching arc length. Matching central angle measure, I'm sorry. Arc length, however, is different. So with arc length, you want to think about string. Arc measure on my clock in the classroom versus on the Allen Bradley clock would be the same between 3 o'clock and 324. What would not be the same, though, is the physical length in feet, inches, miles, centimeters that a string would take if we laid it upon that arc. Those arcs would be equal in measure, but not equal in arc length. They would not be congruent. So when we dilate a circle, we make it go from a smaller circle to a larger circle, stretching it in that 90-degree directions, or in 2 different directions that are 90 degrees apart. What would change and what wouldn't change? So the measure of arc AR in this picture, no matter how big or how small I dilate the page, that measure of arc AR is going to remain 90 degrees. The length, however, of arc AR is going to change. Here it is smaller, and here it's larger, even though the angle measure has not changed. So the length of arc AR, that is going to change under dilation. This is why this clock in my room will still travel the same number of degrees for that minute hand in 24 hours, but it won't travel the exact same distance or length along the arcs. So arc length. The length of an arc is part of the circumference. So the length of the arc equals, and at first we're just going to say some fraction of, we're going to say circumference, and then we're going to put more kind of formulamatic ideas to it. That fraction is sometimes represented in things like minutes, 24 out of 60 minutes. It can also be done in degrees. So one way that arc length is sometimes calculated is its arc measure over 360 degrees, so that we can figure out what fraction of the circle an arc is taking up, multiplied by the circumference. But that fraction doesn't have to be done in degrees. That fraction could be done in minutes, like the Allen Bradley clock idea. That fraction could be done in all sorts of different measurements, so that we could just figure out what part of the circle we were referring to, instead of the whole circumference. So in A, B, and C, just to get us used to this, what fraction is it taking up? So some are going to be easier to tell than others. So arc AB in this circle is taking up 1/4 of the circle. We are so used to 1/4 of the circle being a right angle in there. But really, if you want to go back to that idea of arc measure over 360, that arc's measure is 90 out of 360. Reducing the fraction so we can do good mental math in these is also one of the goals of this section. Arc CED here is definitely, its endpoints are a diameter, so what fraction of the circle is it taking up? 1/2. or 180 3/60ths. But again, seeing where we can reduce that so the mental math will be easier to work with. Arc EF here is 120 degrees in arc measure, so there are 3 120-degree angle or arcs in every circle. So if we wrote it this way first, again, for mental math, making this easier, we have a third of the circle. So if the radius of a circle is 24 centimeters and they tell us the measure of one of the inscribed angles, should we be able to figure out this arc length? Well, sure. So we said arc length is some fraction multiplied by the circumference of the circle. So what fraction is it taking up, and then what's the circumference of our circle? So let's see what we can fill in and then go calculate. So if I start to look at my circle, the measure of arc BTA is the major arc that goes around like this. So this is a lot of good arc and angle review. I do know that the angle out here would be, or the arc out here would be 120 degrees because of the inscribed 60. So the arc measure we're looking at in order to calculate the arc length would be 240 degrees, or 2/3 of that circle. And instead of circumference, I'm going to actually put in our correct circumference. And if our radius is 24 centimeters, our diameter is 48 centimeters, so 48 pi centimeters is our circumference. So in order to calculate how many centimeters of length of string it would take to go around here, I'll need to find its arc measure, 240 degrees, relate that to what fraction of the circle it's taking up, 2/3, and then multiply. Here's where I want you practicing good mental math, not reaching for your calculator. Nothing in here said to approximate, so we actually want to calculate this exact and leave it. So 48 divides by 3 16 times. So 48/3 is 16 over 1. So this really turns into 2 times 16 divided by 1, 32 pi centimeters. A lot of the ones that are not asking for approximations should be tried by mental math so that you get that practice. It will be expected on tests and quizzes that you can handle some of those fraction calculations as another part of the skill set that we're working on. In the second example here, they give us some information. They tell us 10 pi, that's actually an arc length. And then they also show us that there's 150 degrees in arc measure to that arc as well, and they'd like us to find the radius of the circle. So again, I would set the idea up that arc length always comes from some fraction of the circumference of the circle, some part of the entire distance around, and let's see what we can fill in for this particular situation so we can find it. We know 10 pi, they did not give us units, is the arc length. We know it comes from 150 of the degrees of the circle, so 150 3/60ths right away, recognizing those both as multiples of 10. I'm going to simplify my fraction. I could take that and simplify it even more in a minute. And I don't know the circumference, but since I want radius, I'm going to put in 2 pi r so that my formula will calculate radius right away. Part of the hidden curriculum, not so hidden, is to work this out without going to our calculators. So I'm going to keep the 10 pi on this side. And on the other side, I'm going to see what I can reduce or make simpler to work with. So 15/36, and I also have a 2 here. So I could make this 30/36 and then reduce. And if you need to take it over on the side so we don't see all that, we don't think that you're making bad algebra choices here, 30/36, both divisible by 5, divisible by 5, or sorry, both divisible by 6. So 5/6 is my equivalent. So I have a 5/6 pi r on this side. Then again, I would divide both sides by pi right away so that I've got 5/6 r. And finally multiplying both sides by 6/5 in order to calculate my radius. On this side, I would do 10 divided by 5, which is 2, times 6, which is 12. And I don't know our units, so we're just simply going to say our radius is 12 units long, whatever the units had been for the arc length. So your arc length assignment for 9-6 day 1 is 1 to 9 odds. And then 22 and 24, make sure all algebraic work is shown. Please keep in mind that we're encouraging you to practice mental math to be prepared for the way you'd be assessed on some of these, or some of the types of things we also would expect you to be working on. And then keep in mind that from now on, we would be expecting that you'd be putting things in exact form without being told. The only time you would approximate is if it's mentioned or if it's for the situational context of the problem.